Here are the answers to the quiz on experiences 1 and 2 on the periodic table. The first question, Dmitri Mendeleev is the father of the periodic table. He was the first to really start organizing the elements and focusing on their properties, at least ones that they knew of at the time. But he wasn't afraid to leave some gaps in his periodic table for undiscovered elements. He really tried to match the elements in groups based on their properties. And so if he found that, gosh, there's a couple groups here where I don't seem to have the right element to fill in this spot, but now the next known element seems to match in the next group, he wasn't afraid to leave some missing gaps in his periodic table. And he was very much correct in doing so, right? Number 2, in general, we should know on the periodic table where to find metals, nonmetals, and metalloids, and we should know some of their general properties. Metals are ductile and malleable. Ductile meaning you can draw them into a thin wire. Malleable, you can pound them into a thin sheet. They are good conductors of heat and electricity, but they are not brittle. Brittle meaning that they would maybe like crumble if you scratch them with your fingernail. That would be a property of a nonmetal. Metals are most of the elements on the periodic table. I mean, everybody in the first 2 groups, the alkali metals, the alkaline earth metals, then the transition metals in the middle of your periodic table, and even kind of down on the bottom of the P block, these are all metals. There's a small section of nonmetals that are kind of in the upper right-hand corner of the P block. Nonmetals. And then there's these goofy metalloids that are right along this staircase. Usually periodic tables will have kind of like a black line that zigzags down through the P block. And elements along that little staircase are metalloids. They've got properties that are kind of in between a metal and a nonmetal. I mean, you can pound them into a thin sheet to some extent, but if you really try to bend it, at some point it's going to crack. They do conduct heat and electricity, but just not to the extent of a true metal. I mean, that's why often we call metalloids like silicone semiconductors, and maybe we mix them with other things that we can really tweak the exact amount of electrical conductivity or conductivity of heat. Aluminum is a metal, potassium is a metal, and carbon is definitely not a metal. If you think about like a chunk of charcoal, that's carbon. It's not metallic. You can scratch it with your fingernail. Question 4, the alkaline earth metals are group 2, and here's how I remember it. Alkali metals are group 1 because it's one word, alkali. Alkaline earth metals are group 2 because it's 2 words. So element C would be an alkaline earth metal. There, I'll put that down on the bottom. It should be element C. Number 5, which letter represents an element with 2 valence electrons? It should be your alkaline earth metals. And so we kind of looked at valence electrons in the last unit, the electrons on the outermost energy level. But there are trends on the periodic table. Everybody in the first group, all of the alkali metals and hydrogen, will have 1 valence electron. I'll mark this in blue. Valence electrons. They'll all have an electron configuration that ends something S1. I mean, obviously, hydrogen will be just 1 S1. Lithium would end 2 S1. Sodium would end 3 S1, and so on. So, I mean, obviously, as you go down the group, the outermost level increases, but there will always be 1 electron in that outermost level. In the second group, everybody has 2 valence electrons. All of the alkaline earth metals have 2 valence electrons. Their configurations will all end something S2. Now we skip the transition metals, and the word transition obviously means like a change, and we'll have to deal with them later. Transition metals can be a little bit funky. When they fill these d orbitals, sometimes it's really hard to predict how many electrons are in the outer shell. They're a little bit less stable, and they don't follow trends as great. And transition means like a change, and Sometimes they can have different amounts of electrons in their outer shell. Just kind of depends on their mood or their situation, what they might be bonding with. So we skip the transition metals. But then when you hop back over to the p block, technically the first group in the p block is just called the boron family. But everybody in that group will end something S2, something P1, for a total of 3 valence electrons. The next group would be the carbon family, where everybody will have a configuration that ends something S2, something P2. And carbon would be 2S2, 2P2. But there will always be 4 valence electrons. Everybody in the nitrogen family will have 5 valence electrons. The oxygen family will all have 6. The halogens will all have 7. The halogens will all have a configuration that ends something S2, something P5. And fluorine would be 2S2, 2P5. Chlorine would end 3S2, 3P5, for a total of 7 in the outer shell. And then finally, when you get to the noble gases, we say 8. Most of the noble gases will end something S2, something P6. All the orbitals are full, and that's why the noble gases are non-reactive. Full orbitals is really stable, so they don't need to react with anyone to try to fill their outer orbitals. They're already full. Now, obviously, one of the exceptions would be helium, because he's only filling the 1s with 2, but he's still non-reactive because that's all that fits in the first energy level, just an s orbital with 2. So usually we say the noble gases have 8 valence electrons, but obviously helium only has 2 then. And so C would be in the group with 2 valence electrons. Question 6, the similar chemical properties come from having the same number of valence electrons. Same number of valence electrons. It's the electron structure that impacts chemical changes and chemical properties. So the nucleus is cool, but we can't really do nuclear reactions in our lab. But we can do chemical reactions. We can change the electron structure. And so if the outer electron structure looks the same or similar, we should expect similar properties. And so going up and down in a group, B and E are both halogens. They would both have 7 valence electrons, and we would then expect that they would have similar properties. And that's why all of the alkali metals have some similar properties. They're all reactive with water, which is a strange property of a metal. Well, it has to do with the fact that they all have a very similar outer electron configuration. 1 valence electron, there's something really reactive about only having 1 valence electron. Eventually, we'll kind of figure it out. And we're getting to the end. Number 7, valence electrons and core electrons. And so we kind of even mentioned this in the first unit on atomic structure, but it really comes back again when we look at trends in properties on the periodic table, and that we want to be able to look at an element and quickly determine how many valence electrons versus core electrons. Are these atoms going to have similar properties, different properties? And so sometimes it helps to think about the electron configuration or even an orbital diagram with arrows and boxes if you like those. I just wrote the electron configuration. The valence electrons are all the electrons in the highest energy level, not just the last orbital, all of them in the highest energy level. So anything in the 3rd energy level. So I should have a total of 6. And then all of the inner orbitals that are nice and full, those are my core electrons. So sulfur is element 16. There are 10 core and 6 valence. And then finally, Coulomb's law. I'm obsessed with Coulomb's law. Now, there is an equation on calculations with Coulomb's law, which I will never ask you to do. We're never going to quantify Coulomb's law, but qualitatively, I should be able to figure out, is this an attraction, a repulsion? How strong is the attraction? Here in number 8, Because these particles are both the same charge, they will repel. Like charges repel, whether it's positive, positive, or negative, negative. I don't care the magnitude of the charge. Like charges repel. Number 9, which of these should show the greatest force of attraction? Okay, well, number 1, opposites attract, likes repel. So if I ever see anything that's like charge, like that +2, +1, even though they're really close to each other, and normally we think about strong attractions where the particles are really close to each other, I think maybe they were just trying to throw us off with this choice here, and that, oh, wait a second, they won't even attract each other. They're going to repel. I mean, as soon as they can, they're going opposite directions from each other. Like, I can obviously force the opposite poles of a magnet to be close to each other, but then they should repel pretty quickly. Okay, so everybody else has opposite charges, so they should show attraction. Then I look for distance and magnitude. And so like the two choices in the middle, a +2 and a -2, a +1, -1. Well, yeah, I've got in the first choice larger charges. The second choice, they're closer together. But then I look at the first choice, and I don't know, this distance is probably pretty close. Nah, it's kind of close. But then obviously in the top choice, I've got a larger magnitude of charge. And so a +3 and a -2 should be more attracted to each other than a +2, -2, or even a +2, -1. So the distance is about the same as the third one down, but the magnitude is greater than either of the two in the middle. And then finally, 10 and 11. So if you kind of think back to the first unit test, it was short answer stuff where the questions are really similar to what you found on these little quizzes within the unit. But when you get to the final summative, you should be able to explain it. I mean, this is all good practice in a pretty non-threatening environment, right? At least I've got multiple choices. It's like I can kind of pick the choice that seems the most reasonable. I'm not totally off in la la land. I've got some choices. But when you get to the final unit assessment, I need to be able to explain this. So a question like 9 might show up and they might say between diagram A and diagram B, which will show the strongest force of attraction? Explain your answer. And maybe I'm going to explain things like, oh, because there's a greater magnitude of charge, or because these particles are closer together. When I see something like 10, now we're just putting real elements in play. Going down a group from lithium to potassium, the force of attraction between the nucleus and the outer electrons will blank because blank. Okay, well, think about the little Bohr models. So here's your nucleus, maybe. Lithium has electrons distributed amongst 2 energy levels. All right, cool. And so here's my nucleus, and maybe here's my outer electron. And because the electron isn't that far from the nucleus, the attraction should be relatively strong. I'll put a little positive in there. There's my positive nucleus. It's going to attract the outer electrons. But then when I think of potassium, potassium has electrons distributed amongst 1, 2, 3, whoa, 4 energy levels. So here's my little electron. Yikes, now it's pretty far from the nucleus, my positive nucleus. Just distance-wise, it's going to have a harder time hanging on to that outer electron. And so it kind of goes back to Coulomb's law in that there are 2 things that affect the attraction of oppositely charged particles. One of them is distance. And so going down a group, the number 1 thing we look at is distance. And so because the electrons are farther from the nucleus in potassium, the force of attraction will decrease. Outer valence electrons are farther from the nucleus. Now, somebody asked a question last week and said, but there are like more protons and more electrons? Yes, you are right. In potassium, there are obviously more protons and more electrons. But those electrons are going farther from the nucleus. And so you've got like two factors to consider. I'm going to tell you right now that the number one thing we consider to be the main determining factor in the force of attraction going down a group, distance. The electrons are farther from the nucleus, significantly farther. I mean, again, the nucleus is like a marble in an NFL stadium. Distance is the number one factor going down a group, and it makes the force of attraction weaker. But going across a group, the attraction will increase. Now the nucleus is becoming more positively charged. The electron cloud is becoming more negatively charged too. But the key is that distance is not really a factor. So again, think about going across a group. Like, let's say I have boron, and boron is element number 5, and then I go all the way across to maybe like neon, element number 10. And so, yeah, I mean, here's 10 protons and 10 electrons. And then, yeah, this poor little guy, he's only 5 protons and 5 electrons. And so, obviously, yes, the more protons in the nucleus, the stronger the magnet, the stronger the core positive charge in the atom. And yes, we are adding electrons, but again, the key is that when you go across, you're not adding those electrons to higher energy levels. You're just filling the second energy level. Oh boy, I think I can squish it in here. You're just filling the second energy level. So distance is not a factor going across. Yes, I'm adding more electrons, but they're all going in the second energy level. So now the reason the attraction gets stronger is because the nucleus becomes more positively charged. It's more strongly attracted to its negative electron cloud. Fantastic. So if there's anything in here that is still kind of bugging you, keeping you up at night, just shoot me an email or a message in Canvas and let me know.